At this point, you should have seen examples of many of the misconceptions that come out about Newton's laws and the concept of inertia and force. In this first part, we want to look at the concept of force as it applies to Newton's first law and Newton's second law. We'll then add Newton's third law in a later video. To really look at this, let's backtrack through a little bit of the history of the way this was considered up and before the time of Newton. First scientist to really put thought to this was Aristotle, and to really give us a theory. Aristotle described motion in two ways, as either natural motion or violent motion. Natural motion was straight up and straight down. It was objects seeking their natural resting place. If something was made of earth, it wanted to rest on the earth, so it would move straight down if released. If something was made of air, like a balloon, it would go up in the air to its natural place. This was not caused by any sort of force. This is just the natural motion of objects. He also described violent motion. Violent motion is imposed motion, motion where you're causing the motion by presenting some sort of external force. This was our understanding for quite a few years. Copernicus, Galileo, and eventually Newton come up with a new understanding of all of this. Aristotle had said the earth must be in its natural resting place and therefore not be moving. Copernicus was the one who started to question this. He started to say that the earth and all of the planets are actually revolving around the sun, not everything else are revolving around the earth. The earth is not in its natural resting place. The earth is actually moving around the sun. He put this out in his book in 1543, which translates the title to On the Revolutions of Heavenly Spheres. Galileo supported Copernicus' idea that everything revolved around the sun. He also got rid of the notion that force was required to keep something moving. This is where we'll see in Newton's first law. Let's describe a force as any push or pull on an object, and we'll go into a lot more detail later in this chapter about all the different types of forces. The reason we commonly see things coming to a stop is because of a force that is being applied, and that force a lot of times is friction. If you roll something across the floor, it's going to come to a stop eventually. It comes to a stop because there is a force being applied to it, friction. Think about ice, which has very, very low friction. On an ice surface, an object will slide for a much, much larger distance because there's much less force. It will keep moving at pretty much a constant speed. And that's what happens when there's not a force applied. So friction is the thing that it's the force that slows objects down. Think about a ball rolling on a ramp. If it's sloped downward, it will speed up. That's because of the force of gravity. If it rolls up an upward slope, it'll slow down because of the force of gravity. When it's on no slope, if you have a surface that doesn't have friction, it will move at a constant speed. Think about it rolling down a hill. At the bottom of the hill is relatively constant speed, and then it starts to slow down going back up the hill on the other side. So if you had something that looked like this, you would see at the bottom going down, it would be speeding up. When it was in the flat section, I didn't draw that very straight, a flat section here, it would be going at a relatively constant speed, and then going up would start to slow down. In this flat section, there's really no force being applied. There could be some friction which would slow it down, but if we take friction away, it would move at a constant speed. This is the concept of inertia. Galileo had found that a body will keep moving forever in its natural state. As long as there's not a force applied, it will just keep moving at a constant speed forever. This is the ability of an object to resist a change in its motion. That's what we would define as inertia. Isaac Newton, who was born on Christmas Day, 1642, which is also the year Galileo died, was the first one to give us these laws of motion. He actually came up with these laws of motion by the time he was 24 years old. Newton's first law is called the law of inertia. It states that every object continues in a state of rest, being zero velocity. So think of rest always as velocity equals zero, or in a straight line at a constant speed. So we can think of that as a large way of describing constant velocity. So in constant velocity, unless it is compelled to change that state by a force being exerted on it. So if there is a total force on the object, a net force on the object will change its velocity. Otherwise, it will stay at a constant velocity. This is hard for us to understand a lot of times because of the fact that we always see things slowing down on Earth due to air resistance, friction, and other forces. It's very rare that we would ever see a case where something had no forces applied to it or no net force applied to it. It's hard to replicate. But what we find is when we do replicate those situations, or when we look up in space a lot of times where we can get a case of no net force, we do see this holding to be true. Inertia is based on the concept of mass. So the inertia is measured in mass. Now, another common misconception that many students have is the difference between mass and weight. Mass tells us how much inertia an object has. The more mass it has, the harder it is to change an object's motion. You can roughly think of this as about the amount of material present. It's always measured in kilograms. And please understand this is not a volume. You can have a pillow and a car battery that have the exact same volume. They have very different masses. Weight is the gravitational force that's acting on an object. How much is the Earth, or whatever planet it happens to be on, pulling on the object? This is proportional to mass, but it is not the same thing as mass. Mass never changes based on location. You have something on the Earth, on the Moon, on Jupiter, in outer space, it's always going to have the same mass and the same ability to resist the change of motion. Weight will change based on the location of an object. It even happens here on Earth. If you were at sea level on top of Mount Everest, you would have a different weight. Mount Everest are further away from the center of the Earth, which means there's less gravitational attraction, gravitational force, which means less weight. Weight is in the units of newtons, or the more common unit that we think of is pounds. Those are force units. It can be found, you can write an equation, F, weight, equals mass times acceleration due to gravity. The weight of an object, a kilogram, would be 9 newtons on Earth. When we hear the term net force, what we're saying is the combination of all the forces acting on an object, the sum of all forces. You see this written as F net. You also see this written as sigma F, sigma standing for the sum of all the forces. Only a net force changes an object's velocity. Individual force is balanced out by other forces. Force and acceleration. To cause something to accelerate, we must have a net force. Net force is always proportional to acceleration. The more force you apply, the more something is going to accelerate. Acceleration is inversely proportional to mass. Think about a car versus you push your friend and you push your car with the same amount of force, the friend is going to accelerate more because they have less mass. This is Newton's second law of motion. The acceleration produced by a net force on an object is directly proportional to the magnitude of the net force in the same direction as the net force, and it's inversely proportional to the mass of the object. That is an equation, F net equals ma. This is one of the most common equations in all of physics and a very important equation for us to use. That summarizes the first and second law. You can really think of this as the mathematical version. F net equals ma. F net is 0. Acceleration is 0, and that leads into Newton's first law. If there's no net force, an object will stay at a constant velocity. There's no acceleration. Next, we're going to look at some examples of this in the next video of example problems on Newton's first and second law.